All right. Hello, everybody, and welcome to the final session of ICCP 2021. I want to quickly say thanks to the organizers for putting together a fantastic conference. I think the hybrid nature of this was pretty cool. I was really interested to see this all play out. A few quick notes. I've been asked to mention that you should stick around on this same stream for the closing remarks for the conference, and that will include announcement of the best poster from this year. Okay, so without further ado, let's get into the final session. We have a very exciting session, which will cover topics ranging from depth imaging to fundamental resolution limits to under-display cameras and video denoising. Our first talk in the session will be titled Exploiting Wavelength Diversity for High-Resolution Time-of-Flight 3D Imaging. This paper was jointly first authored by Feng-Kang Li and Florian Willemitzer from Northwestern. And this is joint work with Muralidhar Madhavushi Balaji, Prasanna Rangarajan, and Ali Kosert. As a reminder, please ask copious questions in the chat, and I will compile interesting questions and ask them during the Q&A at the end. Today's presenter will be Feng-Kang Li. Let's go ahead and watch the video.
Hello, everybody. Thank you for tuning in. In this talk, we will introduce you a procedure to build better time-of-flight 3D imaging cameras. And by better, we mean cameras that can reach higher spatial resolution and much higher depth resolution than conventional time-of-flight cameras. And we will show you that this can be done with a very simple trick, namely by exploiting frequency encoding in the illumination. The work will be presented today by Feng-Kang Li, who was a PhD student in the Computational Photography Lab at Northwestern University, and myself, Florian Willemitzer. I'm a research assistant professor also in the Computational Photography Lab. Let's start with a quick recap how most commercially available time-of-flight sensors work. A light source is rapidly modulated in time with a sinusoidal function, and a special camera detects the modulated signal that returns from the object. Since the light traveled some time through the scene, you can detect this phase shift phi with respect to the clock signal, and from this phase shift and the known frequency f of the sinusoid, you can directly calculate the depth. Of course, you also make an error in the phase estimation, and this error basically defines the depth error of your measurement. As you can see, the depth error is inversely proportional to the frequency, and this is already the basic recipe to reduce the depth error. Go to higher frequencies f. The problem is that due to limitations in silicon manufacturing technology, the largest modulation frequencies that can be achieved with these time-of-flight cameras is on the order of 100 MHz, which results in a depth error of around 1 centimeter. There are alternatives on the other end of the spectrum. There is another time-of-flight principle that is well known in optical metrology, and this is interferometry. And interferometry is not using a modulated light source at all. It's using the oscillations of the physical wave light field itself. So it works with very high optical frequencies, up to hundreds of terahertz, and it's very precise, up to nanometers resolution. But conventional interferometry cannot be used on rough surfaces because the small wavelengths lead to speckle that completely scrambles up the optical phase that would be needed to calculate the depths. So what we really need here is we need a wavelength that is larger than optical wavelengths but smaller than time-of-flight wavelengths, and this is exactly the regime we are operating in for this work. So our approach exploits wavelength diversity. What does this mean? This means if we superimpose two lasers with slightly different optical frequencies, we produce a high frequency wave with a low frequency beat node. And by super heterodyne detection, we are able to electronically isolate this beat wave and to create a low frequency synthetic wave that is now defined by the difference of both optical frequencies and thus can be orders of magnitudes larger. The sensor embodiments that we introduce in this talk to detect the synthetic wave are in principle dual wavelength Michelson interferometers with a focal plane array sensor for detection. And as I said before, if we would look at the phase maps of each optical field separately, we would end up with these speckle fields here, where the phase is completely scrambled and reveals no information about the macroscopic path length variations at all. things change if we take the two fields and synthesize this correlation term here, which contains, as you can see, the difference of the two phase maps. And this term is now particularly interesting because the phase of this term does show a clear structure and is not speckled. And what is in fact happening here is that the microscopic phase perturbations at each single wavelength, they cancel each other out, and the phase map at the end contains only information about the macroscopic path length variations on the order of the synthetic wavelengths. The gag with the superheterodyne detection that we introduce in this talk is that we do not have to capture the fields at the two optical wavelengths sequentially. We can turn both lasers on at the same time to capture the synthetic field directly, and this has great benefits for sensor robustness and speed. For the experimental implementation of such a superheterodyne interferometer, we need to play another trick. We need to frequency modulate the reference arm with a relatively low frequency, and in this case this is done with this cascade of acousto-optical modulators here. And this results in a second beat frequency in our system, new AOM, but this beat frequency is now so low that state-of-the-art silicon detectors can easily log into this frequency and use this to demodulate the high frequency synthetic field that we want from a series of images. And what we will do now is we will introduce you 3 different prototypes which use sensor architectures that differ in log-in frequency and pixel resolutions. However, what needs to be emphasized here again is that in contrast to conventional time-of-flight cameras, the log-in frequency here only limits the acquisition time and not the depth resolution of the sensor. The depth resolution is only dependent on the synthetic wavelengths, which is defined by the beat frequency of the two optical wavelengths of laser 1 and laser 2.
We first use a lock-in sensor to detect the interferogram from the object. The lock-in sensor we used is 300 by 300 pixels. In the lock-in sensor, it has an internal oscillator which produces an in-phase and quadrature phase correlation. The oscillation frequency is the same with the lock-in frequency. The sensor will output 2 readouts, II and IQ, and we computationally square each of them and then combine to get the depth information encoded with synthetic wavelengths. In the end, we will do full phase shifting and then compute the depth information of the object.
Hello.
With the lock-in implementation, we first verify experimental upper bound performance by repeatedly imaging a planar cardboard. The cardboard has an optically rough surface. We repeat imaging the object for 50 times and then choose a valid point and quantify the RMSE for 4 different synthetic wavelengths. As we can see, smaller synthetic wavelengths demonstrate better depth precision, and we can get a depth precision as small as 35 micrometers from this experiment. The theoretical upper bound for this technique is actually limited by the object's surface roughness.
Hello everyone.
Then we image a plaster bust which is about 10 centimeters in height. We can clearly observe the spicules from the sensor readout. Although there is a spicle in the intensity map, we can still reconstruct the phase maps with different synthetic wavelengths. During the measurement, we use a large synthetic wavelength of 121 mm to generate a phase map without wrapping. And then we use this phase map as a guidance to unwrap the phase maps measured with smaller synthetic wavelengths. Once we reconstruct the phase map, we can generate the corresponding depth maps. We also show a rendered depth map, and we can see the eyes and the nose of the bust. However, the details are not very clear due to the limited spatial resolution. To increase the spatial resolution, we then implemented a capture system with a flutter shutter camera. Flutter shutter is a special operation mode of a CCD camera. It works similarly to a lock-in camera. The flutter shutter camera captures the interferogram in the front of the sensor plane. After one exposure, it outputs an intensity that encodes depth information. We use the full phase shifting method to estimate phase and amplitude of the wavefront for a single wavelength. We sequentially estimate the wavefront for lambda 1 and lambda 2. After acquiring the wavefront at least two wavelengths, we can computationally combine them to generate the depth map from the synthetic wavelengths.
Hello.
Here is an experimental verification using a flutter shutter camera. This is the phase map, and here are the render depth maps from different view angles. Fine details can be observed from this capture compared to that with a lock-in sensor. We high-pass filter a 200 by 200 pixel region and quantify the MSE to be about 376 micrometers, which demonstrate a high quality of the measurement.
Hello.
Lastly, we implement the proposed 3D sensor with an off-the-shelf CMOS sensor to remove the requirement for high lock-in frequency needed in lock-in and flutter shutter sensors. Here, we treat each pixel of the CMOS sensor as a temporarily resolved photodetector with a detection frequency around 20 Hz. After the sensor records a video of the interferogram, we square the temporal signal and apply temporal filtering to extract the signal encoded by the synthetic wavelengths. In the end, we computationally estimate the phase at the synthetic wavelengths from which we compute the final depth map. With this implementation, we image a tilted rough metal disc at 3 different synthetic wavelengths. Again, smaller synthetic wavelengths provide a better depth precision, as we can see when we compare the blue line of 1 mm synthetic wavelengths with the red line of 6.5 mm synthetic wavelengths. Now let us compare the performance with different sensor architectures. APD represents a single pixel avalanche photodiode, which we demonstrate in our ICCP 2018 work. Compared to APD, the focal plane methods proposed here remove the need for point scanning. Compared to a lock-in sensor, flutter shutter and CMOS sensors provide much higher spatial resolution. Currently, the flutter shutter implementation is the optimal solution with the best performance. To summarize, we introduced a new method for high-resolution time-of-flight 3D imaging. The method exploits wavelength diversity and measures objects at a synthetic wavelength that is freely tunable. We introduced 3 different prototypes, all using different sensor architectures. With these prototypes, we demonstrate that a depth resolution below 100 microns is possible, while having cheap resolutions in the megapixel range. This is significant improvement compared to the state-of-the-art time-of-flight sensors. What we did not cover in this talk is a question about fundamental performance limits. Questions of interest can be, for example, what is the smallest possible synthetic wavelength? Do pixel size and spikel size influence the reconstruction result? Or, which sensor architecture is the most favorable one in terms of SNR? For these questions, please refer to the following papers for more details.
Hello.
Thank you for listening, and feel free to let us know if you have any questions.
Okay, thank you for the really fascinating talk. I have the author Feng-Kang Li here, ready to ask questions. So as a reminder, please type your questions into the YouTube chat, and we will be happy to field them. While we wait for you to do that, I can ask some questions. It's been my experience with interferometers that they can be fairly vibration sensitive because you're relying on stable fringes. Does this have a similar issue to that?
So in our approach, actually, since we're using the synthetic wavelengths, so because the synthetic wavelength is much larger than the vibration range, right? So because the synthetic wavelengths we're using like tens of centimeters or like so that's much higher than the vibration like range. So it's not a problem in our approach. Yeah. So we know it's actually a very challenging problem for the interferometry system with the single wavelengths, right? Because the single wavelength is just like 100 nanometers, right? So that's pretty sensitive to the vibration. But in our approach, it's not that sensitive to the
Yeah, very cool. Yeah, that makes a lot of sense. So let's see. So another question I had is, so I think you mentioned in the paper that you have some robustness to background illumination because of the fact that you can sort of lock into the synthetic frequency, right? Have you tested this in like broad daylight? What's sort of the limits of that range of how much background to signal you can actually withstand?
Sure. Yeah, I think that's a good question. So we haven't like checked that with with some experiments, but we actually when we do the experiments, we are actually turning on the light in the room. So actually, there's definitely some like ambient light, strong ambient light in the room condition, but still that's not a problem in our system, as you said, because we're using the locking technique, right? So we are kind of reject the background. Yeah.
I see. Okay, so still some testing to do maybe for the limits.
Sure, yeah.
Okay, but yeah, that's very cool. Okay, a question from Ori Katz in the chat. He says, thank you for this very nice talk. How does this approach compare with flash LiDAR?
Flash LiDAR, so basically in our approach, is still continuous wave time of flight. So I think the flash LiDAR he mentioned probably is the pulse wave LiDAR. So it's still like sending a pulse to the object, and then you're detecting the pulse to calculate the depth. But in our approach, we are actually using the continuous wave. So it's not a pulse wave based. Yeah, but that's a good question. Yeah.
I see. Interesting. Okay, well, I think we are just about at 15 minutes. So if there are further questions, please ask them in the chat and can follow up in text. But let's move on to the next talk.
Thank you.
Yeah, thank you. Great talk. Okay, so the next paper that we'll have is titled Designing Display Pixel Layouts for Under-Panel Cameras. This is by Anki Yang and Ashwin Sankarana Rayanan. I think I got that close to right. And this was this year's best paper from ICCP 21. So this is very exciting. So the speaker will be Anki Yang. So let's go ahead and watch the presentation. And as a reminder, please put your questions in the chat.
Hello everyone. This talk will be on designing display pixel layouts for under-panel cameras. Most of today's mobile devices still reserve a space on the top of the screen to place the front camera. With today's trend of having large screen-to-body ratio, an urgent question is, can we hide the camera onto the display but still have access to high-quality photographs? OLED displays, commonly used in mobile devices, can allow light to pass through openings in it. Here, we can see two commonly used OLED displays. The black regions contains RGB pixels and circuits, all of which block light. White regions are additional space that are transparent. These regions can let light pass through. This feature opens a whole new opportunity to place the camera behind the display, and many new degrees of freedoms comes along. For example, the location, the aperture size, and potentially the whole screen can be used for cameras. Let's take a look at a photograph captured with one such under-panel camera. Surprisingly, the captured image is blurred significantly. To understand why this is the case, let us take a look at image formation of an under-panel camera. In an under-panel camera, we have a lens and an image sensor observing a scene through the openings of the display. This display acts as an aperture on the lens, and it has features in the orders of tens to hundreds of microns. These features diffract light, which result in large blur. Under some assumptions, we can express the blurred image as a convolution between the desired sharp image and a blur kernel K, which is given as the scaled power spectrum density of the pattern describing the openings of the display. Due to the small features on the display, the size of this blur kernel is large, often spanning hundreds of pixels in the image plane, which results in a severely blurred photograph. This large blur is also hard to deblur. Here is the image after deblurring using Wiener deconvolution. We can see severe raining artifacts along the vertical edges as well as the bricks. The goal of our work is to design a display in terms of its openings, such that it produces an invertible blur kernel. Let's first understand how different features of the display affect the blur kernel. The openings on the display panel can be constructed by using a single pixel and periodically tile it over the entire panel. We will keep our focus on these two components: the per pixel opening pattern and the pixel tiling method. We first investigate display pixel tiling method. Conventional displays do periodic tiling, that is, all display pixels are identical. We show in the paper that periodic tiling is not conducive to having a compact invertible blur. Based on that insight, we propose to randomly tile the display pixels. At each position, we randomly rotate and flip the original pixel. For a directional per pixel opening, periodical tiling induces a directional blur kernel. This blur kernel is compact in vertical direction and very flat in horizontal direction, meaning that horizontal features will be extremely hard to recover. For the same directional pattern, random tiling produces a blur kernel that is equally invertible in both directions. We provide a theoretical derivation for the expected blur kernel and its effect in the paper. On the whole, random tiling improves the invertibility of the resulting blur kernel. The second factor that affects the blur kernel is the opening pattern at individual pixel. This per pixel opening pattern is critical in determining the overall shape of the blur kernel. Here, TOLED is narrow in horizontal direction, thus it induces a wide blur in horizontal direction. If we rotate TOLED pattern, now it is narrow in vertical direction, and thus the blur is wide in vertical direction. We can see that a directional unit opening will result in a directional blur kernel. If we use an isotropic pattern such as POLED, the blur kernel is more isotropic as well. Thus, in the second change to a display layout, we optimize the per pixel pattern such that it produces an invertible blur kernel. During optimization, we first tile M periodically to form the display panel and compute the blur kernel K, and then we use the blur kernel to compute losses. We formalize an optimization by this target function. The variable we optimize for is the per pixel pattern M. M is a matrix. Each element of M represents the opening at that position. Thus, each element is mapped to between 0 and 1. 0 is completely closed, 1 is completely open. The first term is PSF-induced invertibility. This term only involves the blur kernel K. The second term is data-induced invertibility. We apply blur kernel to images, and blurry images need to be invertible. The third term is area constraint. C is the desired opening ratio. We need to guarantee that there are enough closed space to place RGB subpixels and circuits. As a summary, to make the blur kernel invertible, in this work, we propose two innovations. The first innovation is to change the periodic tiling into a random tiling. This produces more invertible blur kernels. The second innovation is to optimize the per pixel display pattern. We further combine the first and the second design, optimizing pixel openings with random tiling, which achieves the best performance. On the whole, the new blur kernels are more robust to inversion and produce much better deblurring results. Here is our under-panel camera prototype. We print photomask to emulate display panels, and then place the mask tightly against the rear camera of a cell phone and take pictures by accessing the touch screen. This mask is printed at resolution of 4 microns and emulates displays at 300 dots per inch. Next, I'll show some results captured using this prototype and deblurred using Wiener deblurring. This example demonstrates the effect of our two designs. We capture two toys sitting on the grass. The first column is the baseline layout, conventional TOLED. We can see that there are severe horizontal artifacts in the recovered images. Next, we introduce random tiling to the same TOLED pattern. We can see that horizontal artifacts are suppressed, and we can see more details, but there are artifacts around the head and feet. Keep random tiling. We further optimize the per pixel pattern. We can see that the artifacts around the head and feet are further suppressed, meaning that optimization yields another performance boost. In the following examples, we compare two conventional displays with our layout, Again, all images are deblurred using Wiener deconvolution. These are the images captured from TOLED. The left image is captured under TOLED, and the right one is the corresponding deblurred image I showed earlier. Again, we see repeated lines along vertical edges. This is the image from Penta-OLED. POLED yields better deblurring results than TOLED, but we can see purple halo along the edges of the windows and on the white bricks. Here is the deblurred results from our pattern. The artifacts along the windows are suppressed, and it also recovers more details compared to POLED, for example, the white bricks. Let me compare POLED and our pattern again. POLED and ours. Next, I will talk about several features of under-panel cameras in our design. First, our display layout is better than conventional displays, regardless of deblurring methods. These two images are captured under TOLED display and deblurred using Wiener deconvolution and DeepNet respectively. DeepNet improves the image quality by introducing more details and less noise, but it also produces unexpected artifacts in the wall. These two images are captured under our pattern. Left is from Wiener deblurring, and right is from DeepNet. Again, DeepNet is slightly better. It's worth emphasizing that even using Wiener deconvolution, our display layout still outperforms DeepNet results of the conventional display. To verify this, again, here is the TOLED results, and here is our results. Second, for under-panel camera, the blur kernel functions are nearly constant across different depths. Here we show an example of a bear that is focused at different distances from the camera, from 3 meters to 10 centimeters. We can successfully deblur all of them using the same blur kernel captured at infinity. Here, after deblurring, bears looks consistently clear at different depths. While random tiling provides appealing improvement for under-panel cameras, current display technology hasn't able to produce randomly tiled display. We provide a detailed discussion in the paper. We argue that this is an engineering challenge and can be accommodated in the near future. All display layouts produces artifacts in the saturated regions. In the second row of this example, the metal produces flares, and all three deblurring results are endowed with artifacts. This is because saturated pixels break the linearity of the imaging model. We can handle saturation using HDR photography. On the left, we show deblurred results from a single exposure image. We can see artifacts around the light source. On the right, we show deblurred image from an HDR image, where light source regions are handled properly. Finally, in reality, the blur kernel is spatially varying. We capture blur kernels that appear on all edges and near corners. And insets show the residue blurs when deblurred with the center blur kernel. We contend that the spatial varying feature can be handled by more complex post-processing algorithms and wouldn't cause severe artifacts in the deblurring results. Thank you for listening.
All right. Thank you for that fantastic talk, Anki. So we have Anki here to answer your questions. So again, please put your questions in the chat. While we wait for that, yeah, it looks like we actually have a question coming into the chat. So let's get started. So Ben Kang Lee asked, thank you for the nice talk. Does it affect the image quality with turning on the screen when taking pictures using a camera under the screen?
That's an interesting question, and it's also very practical. It doesn't affect the image quality when you turn on the screen while taking a picture, because the light is emitting in the opposite direction, and it wouldn't affect the light coming into the camera.
Okay, so you wouldn't expect, for instance, stray light to be a problem or anything like that?
Actually, we didn't test on work. We didn't do a real experiment with the display on, but we didn't expect that to be a serious like a seriously terrible problem.
Got it. Okay, thank you. Good question. So another question from Akshat Dave. So it's great talk. Is there any difference in the screen display quality using the optimized pixel pattern as compared to TOLED?
Yes, that's also a good question. So we propose two innovations in this work. One is to optimize the per pixel opening, and that for that pattern, these set of patterns, we can actually place the RGB pixel exactly the same way as a conventional display. So it would actually have the same quality as the TOLED. The other innovation is a little bit risky. The other one we propose to randomly tile the display pixels, and we haven't seen any commercialized random displays. So that might affect the display quality a little bit. We show a demo in the paper rendering real images on these randomized displays. And it produces a little bit artifact, but the fact that current cell phone cameras have super high resolution, these kind of artifacts should be negligible.
Right, sure. For a very, very high density display, this wouldn't be a huge deal. But if you had like large, very visible pixels, maybe it could. Yeah, that makes sense.
Yeah, exactly.
Okay, I think we have time for one last question. It's from Hiros Koudulakos. So we have two questions here. So first is, how easy is it to manufacture displays with the desired properties? And second, do the proposed display designs affect the performance of the displays themselves? Okay, so we already had that question. So let's just focus on the first, which is how easy is it to manufacture something that meets your design specs?
Yeah, that's a very practical question. Only for optimizing opening patterns, it is easy and very doable in commercial production for now. And for the randomized display, it is a little bit more difficult. But for the fact that we only need to produce a random display for the size of a camera aperture, which typically is around 5 millimeter in size, a circle of 5 millimeter in size, it wouldn't, our hope is that it wouldn't increase the cost and complexity a lot.
Interesting. Yeah. Okay, well, great. Again, fantastic work. So if anyone has further questions, feel free to ask them in the chat. But let's move on to the next paper. So thank you, Anki.
Thank you.
Okay, so the next paper is titled, or the next talk is titled Fundamental Resolution Limits of Snapshot Array Microscopy. And the authors are Kang-Hyun Kim, Mark Harfouchi, Pavan Chandrakanda, and Rourke Horstmeyer. The speaker is Kang-Hyun Kim. So let's go ahead and watch the video.
Hello, my name is Kang-Hyun. I am a first-year PhD student at Duke University. Today, I will present a new imaging system based on a micro camera array. A general challenge in optical design is to create lenses that can form high-resolution images over a wide area. The field of view of most standard microscopes is still relatively narrow, ranging from a few millimeters to several centimeters, while recent work in the area of high-NA objective lens design has brought achievable resolutions over multiple millimeter areas. There has been relatively limited work on expanding the field of view of the microscope without resulting to mechanical scanning. There are a number of compelling reasons why it's useful to have microscopes that offer much larger imaging field of view. For example, it allows one to observe multiple moving specimens or to rapidly inspect large objects during manufacturing, or open up parallelized assays within the biology lab and the clinic. In this work, I will present an approach for extremely wide field of view microscopy that uses an array of micro cameras to directly image from several hundred square centimeters in parallel. Our design, which we term micro camera array microscopy, MCAM, includes 54 micro cameras that are integrated into a large array. I will first discuss primary parameters that the one needs to decide for the MCAM design and derive its key properties. Then I will highlight its versatility with several key demonstrations. We will begin with the initial assumption that all microcameras within the planar array are identical and will be arranged in a uniform grid. The first important parameter is the choice of the digital CMOS sensor to use. A good choice is 10 to 20 megapixel sensors with a small pixel size for better resolution. Here I will define the sensor size as S. The second parameter to select is the inter-camera spacing P, which defines the pitch between the center of each microcamera's CMOS sensor. The third parameter to decide is the magnification M. The magnification can be defined as image size or S or over objective size or field of view, which means we can change the system's magnification by focusing the lens on a different plane. However, practically it's hard to physically place the cameras next to each other in close proximity, which leads to inter-camera spacing P greater than the sensor size S. So we should rewrite this equation like this. And if the one wants to have continuous field of view with the microcamera array, the magnification should be less than or equal to 1, as the sensor size and the inter-camera spacing of each camera should be the same. Moreover, the required magnification is an inequality because in practice, a finite amount of field of view overlap is required between adjacent microcameras for effective image stitching. By having different magnification, we can design different configurations of MCAM for specific usage. The first possible MCAM imaging configuration is multi-view imaging, that images points within the specimen plane with at least 2 or more microcameras. This type of multi-view imaging geometry offers a number of interesting benefits. For example, it is possible to utilize standard techniques from stereoscopic imaging to jointly estimate the depth of imaged objects, or apply photogrammetry software to jointly reconstruct a height map of the imaged object during the image stitching process. Considering the specific goal of multi-view imaging, it's simple to derive the required system magnification. Each microcamera must image across double of sample plane area width P onto a sensor of width S. This sets the required magnification as this. To increase the space bandwidth product of the system, we decrease the sample distance such that the field of view of each camera overlaps only enough for stitching. The required magnification that can achieve a complete mapping of the sample plane is this. This explicitly notes that the magnification when imaging a continuous specimen area must be less than or equal to 1. This design cannot offer depth estimation, which is possible with the multiple imaging, but has higher space bandwidth product and yields higher resolution. Then why can this higher magnification system yield higher resolution? Normally, the resolution is defined by a wavelength and numerical aperture. However, with such low magnification conditions, one must consider the effects of the finite sensor pixel size when determining resolution performance. The system's pixel-limited resolution is easily found by projecting the finite pixel size onto the sample plane. As a result, the higher magnification can lead to higher resolution. To obtain higher image resolutions than what a magnification of less than 1 can offer, the microcamera array can then be used in a tiled imaging configuration. Here, the system does not image across a continuous area in one snapshot. Instead, each microcamera images a discrete, non-continuous sample plane area. Mechanical scanning of the specimen can then be used to fill in the field of view gaps over multiple acquisitions. In this type of tiled imaging configuration, another benefit of the MCAM becomes imaging throughput. Compared to a standard step and repeat imaging with a standard microscope, an array with n microcameras can image a specified surface n times faster, since it has to scan n fewer locations. A second benefit is that of greatly reduced requirements of the motor's travel range, as it only requires to move a distance of intercamera spacing to fill the gap. We built all three different configurations and demonstrated their capability. For all three imaging configurations, we used the same array of cameras. The only difference from each setup is magnification. We used custom-designed abdomen optics lenses and constructed a 9x6 microcamera array. Here are the key specifications for each design. We could accomplish 20, 10, and 2 full-pitch resolution for each design. Unlike multi-view and standard imaging, the tile imaging requires scanning to cover the entire field of view. Here, I plotted the resolution target images from the center and edge cameras. For each camera, I plotted the center and edge field of views. You can see the resolution improvement from the design 1 to 3. Moreover, it shows that the system can accomplish equivalent resolution across the entire field of views fairly enough from the center to edge field of views. We demonstrate operation in each regime in a set of simple experiments. Design 1 has at least 50% overlap between adjacent cameras' field of view and enables the principle of triangulation to convert the lateral disparity of an object to a depth estimate. We have previously developed a feature-free photogrammetric technique that simultaneously registers and stitches multiple images and generates a co-registered 3D height map. This figure shows this technique applied to the overlapped brush strokes of a painting. As a next demonstration of MCAM imaging, we arranged the MCAM to image across a continuous area and included just a small amount of overlap between adjacent microcameras. This design has the highest space bandwidth product for a single shot among the three designs and provides higher resolution than the previous one, as it does not require 50% overlap and enables the setup to have higher magnification. To demonstrate the setup, we put red and green inks, which were mixed with a source to add higher frequency features at the other edges separately. Then we circulated the water with blowing fans and captured images. To achieve better resolution, we built the scanning system, which requires a mechanical scanning due to the higher magnification. The setup requires 5x5 mechanical scanning, or 25 snapshots, to cover the entire field of view. The figure shows a finer tiled macaque brain slides images from this configuration. Today, I present a method for microscopic imaging that uses a densely packed array of microcameras to jointly image across a large area. Thank you very much for listening.
All right. Thank you for the talk. That was great. Very interesting. We have the author, Kang-Yoon Kim, here. Unfortunately, we're having some technical difficulties with video, so we're going to do an audio-only format. If anyone has any questions about this multi-aperture approach to microscopy, please put them in the chat. In the meantime, I will ask some questions. So it looks like in your array of cameras, you were sort of assuming something like a pinhole model in terms of how the magnification would change with depth. Have you considered how you might be able to play with the stop locations of each one of these cameras to maybe help alleviate some of that? Or perhaps could you, in the high magnification case, could you potentially use like a wide, like a fisheye style lens to sort of increase the field of view by playing with stop locations?
Yeah, so we're still kind of building the system, and yeah, so for the high magnification case, we are just designing or the new type of a lens, but not considering that part, but that can be really interesting. Yeah, and yeah.
Okay.
Yeah.
Still under investigation, but possible, you think? Yeah. So another question I had was if you were going to use this for instance, like fluorescence imaging, how would you envision dealing with? So a lot of what makes microscopy work well is controlled illumination. How would you envision controlled illumination working in a multi-lens system like this?
Yeah, that is also a really nice question. So for the overlaps or the standard imaging cases, the parking distance is pretty enough to put the filters and the illumination. And we can also ensure the uniform intensity of the extending the LED by dividing or calculating the energy per pixel base, and renormalize the fluorescence intensity after that. So we can do post-processing. But for the third case, which was the scanning system, right now we are having 3 millimeter working distance, so it's quite challenging to place the emission filter and all the other systems. So we are kind of thinking novel way to deal with that problem.
Yeah, I see. So if you integrated the illuminators and the filters into each lens, would you have any problems in like the overlapping regions with excess excitation or anything like that?
For the filter, we are putting the separate filter for each lens, but for exciting illumination, we are using just 2 separate large LED, huge one. So that's why I said about like different intensity value or fluorescence exciting LED lights, because we're just only using 2 LED side by side, and that might give different power for exciting the for.
Okay. Yeah. All right. Well, thank you. Very interesting. We're about out of time for questions. So if anyone has more, please again put them in the chat. So thank you, Kang-Yoon. We'll move on to the next talk. Okay. So the next talk is titled Depth from Defocus with Learned Optics for Imaging and Occlusion-aware Depth Estimation. This paper is by Hayato Ikoma, Cindy Nguyen, Chris Metzler, Yifan Peng, and Gordon Wetstein. The presenter will be Hayato Ikoma. So let's go ahead and watch the video.
Thank you for joining us today. I'm Hayato Ikoma from Computational Imaging Group at Stanford University. I'm going to present our project on Depth from Defocus with Learned Optics. As you may know, depth estimation is important in many computer vision applications. The depth measurement is often performed by a device with active illumination, but such devices need complex electronics and they become expensive and bulky. In addition, the depth map is often used as a supplement to an RGB image, so we need another camera to capture a conventional image. So if we can do the depth estimation from a single camera, it's going to be better. Depth estimation from a single image or monocular depth estimation became much better with CNN. But if we don't have any assumption on the scene, the monocular depth estimation cannot estimate the absolute depth. If we have just an all-in-focus image, there is no way to disambiguate if the object is small and close or it's just big and far away. This issue is known as a scale ambiguity problem. But the situation changes if the image has some optical blur. The blur encodes some depth information so that we can estimate the absolute depth from the blur. So our question is, what is the best optical encoding for the depth information? To answer this question, we can perform the end-to-end optimization of the imaging system. By using differentiable programming, we can jointly optimize optics and computation, and this method has been applied to many computer vision systems. Monocular depth estimation is also one of them, but all of the previous works were focusing only on the depth estimation and sacrificing the RGB image. And they had some limitations. Their image formation model was not very accurate, the search space of the optical encoding was limited, and they were not using the knowledge of the image formation model for the depth estimation. So we overcome these issues with our method. Our system jointly estimates a all-in-focus image and the depth map from a single coded image. And we accurately simulate the capture process by considering the occlusion, which was not done in the previous works, and we use a computationally efficient PSF model. And we do the preconditioning of the input to the CNN based on the image formation model. And to jointly optimize the computation and the optics, we can iteratively compute the loss function and update the parameters of the CNN and the optical simulator. And I'm going to go over the details step by step. Let me start with the image formation model. We render the shallow depth of field image in multiple ways. The left one is the ray tracing from 3D models. The next one is computed with a linear model from a pair of RGB image and a depth map. And the linear model is formulated as a sum of 2D convolutions between the depth-dependent PSF and a multi-layered representation of the RGB image. And as you can see, it is mostly correct, but we can see line artifacts in the middle of objects. And also, we can see the blur around the occluded objects are not realistic. And to avoid these issues, we use the front-to-back rendering approach to consider the occlusion. This is often used in computer graphics community, but we cannot directly use it because we don't have information behind the objects. But if we do a proper normalization, we can suppress the artifacts and produces almost identical image to the ray tracing. I don't have time to go over the details of the math, so please check our paper if you are interested. The next one is a representation of the optical components. We are thinking of a camera which has a DOE on the aperture plane of the lens. The most naive way to parameterize DOE height map is to discretize it as a 2D image and treat each pixel as a learnable parameter. The next way is to represent it as a linear combination of some basis functions like Zernicke polynomials and set the coefficients to be learnable. But these two representations requires huge amount of memory because we need to compute 2D FFTs for many times to simulate the whole PSF. So this is why we are introducing another representation with rotational symmetry. We can specify the height map with a 1D vector. It's a simple representation, but introduces multiple computational benefits. If the DOE has the rotational symmetry, the PSF also becomes rotationally symmetric. To simulate the PSF, we need to compute the 2D Fourier transform of a pupil function with a defocus factor. But if we have a rotational symmetry, the computation reduces to an integral of the pupil function and the Bessel function. And if we assume each ring of DOE is sufficiently thin, we can approximate it to a form which we can conveniently evaluate. It is a bit difficult to see until you implement it by yourself, but this form allows us to compute a 1D PSF as a single matrix vector product. After computing this 1D PSF for all of the wavelengths and the depth planes, we can copy the values to simulate the whole PSF. It has multiple advantages, one of which is the memory efficiency, because most computation happens in 1D, and this allows us to use finer resolution of DOE, and it's also fast because the matrix vector product is relatively small and most of the part can be pre-computed before the training. And also, it is suitable for representing quick transition of heights as opposed to the Zernicke polynomial representation. So now, I'd like to talk about the preconditioning of the input to the CNN. The most naive input to CNN is a coded image, but we don't want to completely rely on CNN for the estimation. As I show here, the linear model is mostly correct, so we use this simple model to precondition the input. Basically, we consider the occlusion to simulate the coded image, but solve the linear least square problem to produce a volume which we use as an input to the CNN. This is not very straightforward to compute this solution, but there is an efficient way to solve it in a closed form. But it's an ill-posed problem, so the estimated volume doesn't become sparse. But we can see the texture becomes sharp when they are in the correct depth plane. So what CNN needs to do is to find a plane where the object is really sharp. And I'm going to show this preconditioning is really effective in an ablation study. So now we are comparing our method against previous works. Our method is the only one which jointly estimates the all-in-focus image and the depth map, so we are visualizing the captured image for all previous works, but the estimated image for our method. And these two columns are showing the results from fixed PSF. You can consider all-in-focus is the monocular estimation. And as I was saying, all-in-focus loses the absolute depth information, so that's why it didn't perform well. And the depth from Defocus did a good job because it has some depth skews in its blur. And these are showing the results from the end-to-end optimization. We trained the previous models with the image formation model, which they were using in their paper, but did an inference on the image simulated with the occlusion because it is what should happen in reality. And that's why all previous methods failed at the edges of the object. And as you can see, our method worked really well. And we also compared our method with and without the input preconditioning. And you can see the preconditioning improved the results significantly. So now I'd like to show the results from the prototype. We optimized a system for the depth range of 1 to 5 meters, fabricated the DOE, and mounted on the aperture plane of the lens. The top figure is showing the comparison between the designed PSF and the captured PSF, and of course there was some difference between them, so we fitted our PSF model to the captured PSF and retrained the CNN with the fitted PSF. This is a collection of the results on static scenes. We captured a couple of indoor and outdoor scenes with and without the DOE, and ran the inference on both images. As you can see, the monocular depth estimation completely failed because our CNN has a relatively small receptive field. But our method worked well on all of the scenes, and our estimated all-in-focus images are almost perfect. And the plant images are even difficult for the human eyes to estimate the depths, but our method performed well on these images too. And we designed the PSF with the good size of the aperture, which allowed us to do the estimation on the video. We compared our method with the monocular depth estimation with our CNN, and also one of the state-of-the-art CNN models, MIDAS. As you can see, MIDAS produces good depth maps, but showed flickering because they cannot estimate the absolute depth. But our method produces consistent depth and also recovers fine details of the RGB image. We had a creepy artifacts on the eyes of the lion, but it's coming from the saturation of pixels. This project was a collaboration between myself, Cindy Nguyen, Chris Metzler, Evan Penn, and Gordon Wetstein. Thank you again for listening.
All right. Thank you for the great talk, Hayato. So let's see if we have any questions in the chat. If anyone has questions, please put them in the chat. While we wait for that, I have a few questions for you. So one of them is about doing end-to-end design from RGB data sets using diffractive optics. So diffractive optics are very spectrally sensitive, and I could see a lot of interesting chromatic effects in your design. Do you expect there to be any problem training on something that only has 3 color channels and then trying to adapt it to the real world where the spectrum is continuous and could have more complex features?
Yeah, sure. That's a really good question. I think we didn't show it in the paper, but I have computed the PSF for much finer spectral resolution, and we didn't see the too much difference between the center wavelengths of the RGB channel. So that's why we decided to do the end-to-end optimization for the 3 channels. And yeah.
I see. Okay, so you think your designs are tending not to have a lot of spectral variation. Is there any regularization that's forcing that, or is that just an observation?
It's an observation. We are not doing any regularization for the PSF for the spectral channels.
I see.
Yeah.
Okay, interesting. And then the other question I had is about bridging the gap between like an end-to-end design and an as-built system. So what you built looked, to me, impressively close to what you designed, but with some subtle differences. And you mentioned that you had to fit to that and retrain. So did you get similar performance using the as-built design, at least in simulation, or was the design you were forced to due to fabrication constraints significantly worse than what you wanted?
That's a bit difficult question to answer because in a real system, we don't have the ground truth depth measurement for all over the scene. So we cannot quantitatively evaluate the performance in the same way as in the simulation. But we are showing the quantitative measurement result on the prototype in our paper. And it performed really well. So I believe it's okay.
I suppose my question was at least when you had to retrain, that meant running simulations with your best guess at what the real as-built PSF was. So at least in simulation, you could maybe do apples to apples comparison, right? Between your calibrated system and what you designed.
Yes.
And was there a big difference in performance, at least in simulation? Or was the design you ended up with similarly good quality to what you wanted?
Probably I'm not understanding the question very well. Would you repeat it again?
Sorry. Yeah, no, it's okay. So I'm just asking. So you did the calibration,
yeah,
and then you fit to the calibration data, and then you retrained, right? Using that PSF, right? So was your empirical performance during training similar to your design, or was it notably worse?
It was similar to the design. Yeah.
Interesting. So you think there's a wide range of designs that would have sort of similar performance?
Yeah, I think so. The CNN absorbs that kind of range, I think.
Very interesting. Yeah, cool. Okay, well, yeah, great talk. It looks like we don't have any other questions in the chat. Again, if there are any more, please feel free to add them. With that, thank you, Hayato. We'll move on to the final paper of the session and of the conference. So the last paper that we're going to have is titled Multi-Stage Raw Video Denoising with Adversarial Loss and Gradient Mask. The authors are Avinash Paliwal, Libing Zhang, Nima Kademi Kalantari, and this is all from Texas A&M. The speaker is going to be Libing Zhang, so let's go ahead and watch the video.
Hello everyone, I'm Libing Zhang. I will be presenting our learning-based approach for video denoising. Videos captured under low lighting conditions are noisy, as you can see here. The noise reduces the visual quality of the videos and negatively affects video processing tasks, such as object detection, object tracking, and compression. Therefore, video denoising is an important problem. There has been a lot of research on video denoising, which I'm going to discuss by categorizing them into 2 classes, RGB video denoising and raw video denoising. A large number of traditional and learning-based approaches have been proposed to denoise videos by modeling the noise using additive white Gaussian noise (AWGN). However, since these approaches are specifically designed to remove AWGN from RGB videos, their performance on real-world videos, which usually have a more complex noise, is suboptimal. To address this issue, a few recent methods propose to perform denoising on raw videos by accurately modeling the noise. Specifically, Chen et al. Proposed to train a network to denoise each frame and enforce the result of consecutive frames to be similar. However, the method does not utilize the information of adjacent frames. Yue et al. Proposed to incorporate the information of neighbor frames by implicitly aligning their features. However, since they implicitly align the images, their method is not able to effectively utilize the information of neighbor frames. A couple of approaches propose to generate a denoiser image from a set of burst images. While these methods are image denoising approaches, they can be used for video denoising as well. Specifically, these methods use a network to estimate a kernel, which in turn is used to combine the noisy images. However, these approaches are limited to the size of kernel and can only handle small motions. Our goal is to design a denoising system that avoids the limitations of the previous approaches. Similar to the recent methods, our system works on raw noisy videos to generate a denoised raw video. This video is then converted to an RGB video using ISP. In the rest of the talk, I will explain our approach by showing the RGB frames. However, note that our method works on raw images. To produce temporally coherent videos, we would like to utilize the information of a set of consecutive noisy frames to generate each denoiser frame. I'm going to explain our approach with 5 frames, but a larger number of frames can also be easily utilized. In contrast to the recent approaches that implicitly align the neighbor frames, we perform an explicit alignment and thus break down the denoising process into 2 stages: alignment and fusion. I'm not going to explain each stage in detail. The goal of alignment is to generate a set of aligned images by registering the neighboring frames to the center frame. So obviously, the center frame can directly go to the aligned stack. To generate each aligned frame, we first generate a flow from the neighbor frames to the center frame, and then warp the neighbor frame to the center frame. This process can be done for all the remaining images to obtain the aligned stack. Then, the aligned stack is fed to fusion components to generate the denoised version of the center frame. The major problem is that, for temporally distant frames, the aligned quality could deteriorate due to complex larger objects and camera motion. Inspired by Tassano et al.'s approach, we address this problem by performing the denoising in multiple stages. Specifically, we use our denoiser to generate an intermediate denoiser frame by processing 3 consecutive frames at the first stage. The intermediate denoiser frames are then used as input to the denoiser in the second stage to generate the final denoiser frame. In this way, the denoiser frame is obtained by combining the information of 5 neighbor frames, but each denoiser only processes 3 consecutive frames, thus avoiding aligning temporally distant frames. Note that if we want to utilize a larger number of frames to denoise each frame, we can simply increase the number of stages. In our system, we use convolutional neural networks to model both the alignment and the fusion stages, and the networks in all the denoisers have shared weights. Next, I'm going to talk about the training. To ensure our system produces visually pleasing results with realistic details, we train our multi-stage denoiser in an adversarial manner. Specifically, we use a discriminator to distinguish the fake results generated by our denoiser from the real ground truth images. Here, the multi-stage denoiser is the generator, and the discriminator penalizes the generator for producing implausible results. Unfortunately, by using a naive adversarial loss, high-frequency artifacts appears in the smooth regions of the generated frames. To see this, let's look at a denoiser frame generated by this approach. I'm going to focus on the insights to better show the problem. As indicated by the arrow, the result of generative adversarial network has high-frequency artifacts in the smooth regions. This is mainly because the discriminator interprets the high-frequency artifacts as real textures. To address this issue, our main idea is to provide additional information to the discriminator to be able to distinguish the smooth regions from the high-frequency areas, and therefore detect the artifacts in the smooth regions. We do this by conditioning the discriminator on the gradient mask. As shown here, the gradient mask clearly detects the high-frequency areas. To condition the discriminator on the gradient mask, we simply concatenating the gradient mask with the denoiser frame. In our system, in addition to the adversarial loss, we also use L1 and VGG losses. The details are in the paper. As shown here, conditioning the discriminator on the gradient mask removes the high-frequency artifacts in the smooth regions. Next, I discuss the process for generating our synthetic training set. We first obtain a set of high-quality 4K videos from YouTube. We then downsample each 4K video to 1080p using a Gaussian kernel. This step mitigates the noise, for example, the compression artifacts. These 1080p sRGB datasets can be synthetically converted to raw domain using a processing pipeline proposed by Brooks et al. We then add Poisson and Gaussian noise to the raw dataset. This process gives us the noisy and clean training image pairs in raw domain. Now let's look at our results and comparisons against state-of-the-art methods. Specifically, we compare our method against the image denoising approaches, DIDN and KPN. We also compare against the video denoising methods, VBM4D, FastDVD-Net, and RVD-Net. First, we analyze the performance of our approach against these approaches on our synthetic 1080p test set. We evaluate the results using PSNR and two perceptual metrics, LPIPS and SSIM. The lower LPIPS values correspond to better results, while PSNR and SSIM higher is better. As you can see, our approach produces overall high-quality results and is significantly better than other approaches in terms of all metrics. Next, I'm going to show comparisons on one of these synthetic videos. This is the noise video. Our approach generates good quality results without any obvious flickering artifacts. Compared to other approaches, we produce a temporally coherent video with more details. Next, we look at the performance on real test sets. This is an outdoor video. We generate sharp results while significantly mitigating the flickering artifacts. Compared to other methods, our results are sharper and has less flickering. In conclusion, we propose a raw video denoising system for effectively denoising high-resolution videos. We achieve this by, in part by using a multi-stage architecture. We showed the advantage of using an explicitly trained flow-based alignment system. We achieved the high texture quality by using an adversarial loss and condition on the discriminator and the gradient mask to avoid high-frequency artifacts. Our results showed significant improvement over existing methods. This is my talk. Here are the acknowledgements. Thank you. I'd like to take any questions.
All right. So thank you for that, the final talk of the conference. I have Liping Zhang here live. So if anybody has questions, please let us know in the chat as always. While we wait for you to type your questions in, I'll ask a few. So one of the questions I had is about noise models. So I saw that you were using a mix of shot noise and read noise. I think that's great.
Yeah.
And I'm curious, do you have to train the model for each unique combination of shot noise and read noise? If you want to deal with very dim settings, can you just use the same trained denoiser that you did at some other noise statistics, or do you have to redo it for every set of statistical parameters?
Oh, we just use I guess just one combination of the short noise and the red noise. The model is based on the previous paper and processing from Brooks. Yeah, just one set. We don't have to adjust the different combinations of red noise and short noise. Yeah.
So you don't need to. So you train it at one setting, and then if you have a scene with different noise statistics, it still works reliably, or?
Actually, we have different levels for the parameters for the short and red. Actually, that's kind of, for example, we have a high level noise and low level. That's we choose that kind of parameters randomly.
I see.
Yeah.
Okay. Yeah, I understand. Okay. Yeah. Thank you. Okay. So another question I had is, if you were imaging like a static scene, something that was just holding perfectly still. So if I remember correctly, you're using 5 frames to denoise each individual frame. Is that right?
Yeah. We don't have to distinguish static scenes. So we just assume that the video have large motion. Yeah, dynamic videos.
Yeah. So I guess my question is, if you were imaging a static scene and you could just say, do something dumb like just average all of the same number of frames that you are using, how would a simple averaging approach do to the performance that you're getting?
Actually, we haven't tested on the static scenes because we just assume that all the reasonable video should have dynamic scenes and large motions. Yeah.
Yeah, absolutely. Yeah, that makes sense. Okay. So it looks like there are no more questions. So I can ask one more, maybe quick one. So how sensitive is the flow alignment part to noise? Like, what are the limits where it's too noisy and there's no hope of aligning your images?
Honestly, our method is depend on the flow network. Basically, we first I like to say it's not that sensitive because we retrained the flow nets using noise images, and it works pretty well on general noise images, either high noise videos or the low noise videos. Yeah.
Yeah, I see. Okay. All right. Well, thank you. So with that, I think we'll conclude this session. So thank you again for your time, Li-Bing. Great talk.
Thank you.
Okay, so that's it. So we're wrapping up this session, but we still have a little bit more to go for the conference. So please stick around, and closing remarks and the best poster will be announced. And that'll be in 10 minutes or so, but on this stream. So go ahead and stay put.
You are live.
Hi everyone, I'm Aditya Pedredla and I'm speaking on behalf of the posters team. This year we have 92 accepted posters. That is more than double the number of posters that we saw in the past ICCPs. Due to the hybrid nature of the conference, for the first time at ICCP, we have used a multiverse platform called GatherTown to host all the posters and also have an interactive experience. 44 out of the 92 posters have also submitted pre-recorded videos. We have posted these videos in the ICCP YouTube channel, which you can view at any time. Finally, based on the people's vote, the best poster award goes to not one, but 2 submissions. One of the winners is poster number 29 titled Visual Vibration Tomography, Estimating Interior Material Properties from Monocular Video. The authors are Betty Feng, Alexander Ogren, Catherine Bowman, Chiara Torayo. The second winner is poster number 35 titled Auto-Tuning Structured Light for Coded 2-Bucket Cameras by Optical Stochastic Gradient Descent. The authors are Wencheng Chen, Parsa Mirdegan, Rahul Kulve, Sanja Fiedler, Roman Genov, Kyriakos Koutalakos. Let us congratulate them for their work and let us also congratulate all the authors of all the posters for their fantastic works and presentations. Now, let us hear from the broadcasting chair, Yanis Kiolakas.
All right, thank you, Aditya. First of all, many thanks to Yoav, Kavita, and Nori for inviting me to be broadcaster. This really was a multi-platform conference. We had broadcast from a physical event, live streaming of virtual sessions, live chat Q&A, and GatherTown poster sessions. And I hope that all of these multiple platforms help accommodate as big of a crowd as possible. And it looks like all platforms had their fair share of participation. We had 300 people register for GatherTown. We reached a maximum of 100 attendees being on GatherTown simultaneously during one of yesterday's poster sessions. And the YouTube videos already have almost 5,000 views. If you missed any of the posters of the sessions, you can add to this viewer count. You should go to the ICCP 2021 YouTube channel, and we have there all of the videos that will remain on the channel indefinitely. And before I close, I wanted to acknowledge a few people. First, we had a lot of student and postdoc volunteers that help us with moderating the live chat, providing tech support on GatherTown, and also they help us choreograph and practice the virtual session that you saw streamed on YouTube. I wanted to acknowledge also Yoav Sekman, who organized broadcasting for the physical event in Israel during Sunday. And lastly, Aditya Pedredla, who, in addition to being poster chair, shared a huge amount of the effort that went into organizing GatherTown and the virtual sessions. So that's all I had. Kavita can go next.
Great. Well, thank you all for an amazing ICCP 2021. I will first, because we're just talking about posters and GatherTown, I want to thank the posters committee, Anat, Matt, Aditya, and Yanis, the broadcasting chair. I mean, the amount of work they put in creating a very fun, interactive event where you feel like you're actually there, even though you're not there, has been astounding. I don't think people appreciate how much happens behind the scenes to make this work. And we're really grateful. Yanis actually said something that cracked me up. He thanked us for asking him to be broadcasting chair. I have no idea we could have had this event without the amazing amount of work he did. So we are very grateful to you, Yanis, for accepting. I don't think you knew you had signed up for this much work. And to Aditya and all of you, I know many of you had to pull together to pull this off. So thank you again. I want to thank all of the authors and participants. This was an incredible experience. You know, we're coming out of COVID and the world situation. There's other chaos going on in the world. Meanwhile, we had this wonderful event at Haifa. I was not there, but Yoav was. 200 people in person. And I'm hearing from so many people. It was so amazing to finally be at a conference talking technical stuff with your friends again. It was, you know, it really is, it gives us hope that we can go back to that world. And I'm hoping we'll get there soon. We also, that was the first day, we also spanned multiple time zones. So thank you all for tuning in from your various time zones after hours. And by looking at the number of people watching on YouTube, you can tell even if people aren't there in the different time zones at that time of the event, they've been watching afterwards and they're going to continue to enjoy the quality of this conference. I mentioned that there was this hybrid event and we would have never done it. It is not customary to thank your co-chair, but I have to thank Yoav. Yoav has just pushed through this event through grit, through difficulty upon difficulty. And I'm very grateful to him, a partner and a brother in this process, as we have been started calling each other as we are going through this. So thank you all for all the work you've done. This concludes ICCP 2021. ICCP 2022 plans are still up in the air, so it's forthcoming and they'll be shared in the future. We hope to meet all of you in person physically soon, and please continue to enjoy the work and the talks because it's all on YouTube. Thank you very much and see you around later sometime. Take care.